For a century, physicists have asked a question so simple it sounds impossible. What if our entire universe is inside a black hole? It's not science fiction. This idea emerges naturally from the mathematics of Einstein's general relativity. Because when gravity becomes strong enough, it doesn't just pull matter inward, it bends space-time itself into a closed geometry. Inside that geometry, time slows space warps, and beyond a certain point called the event horizon, nothing, not even light, can return. That's what happens when a massive star collapses. But here's the strange part. The equations don't stop at the horizon. They keep going. And on the other side of that collapse, they predict another region of space-time expanding smooth and disconnected from the outside world. A region that behaves almost exactly like a new universe. This is not a speculative fantasy. In 2010, physicist Nikodem Popławski from the University of New Haven used the Einstein Cartan theory, an extension of general relativity that includes the quantum property of spin, to show that when matter collapses into a black hole, the spin of fundamental particles prevents true singularity. Instead of infinite density, the collapse rebounds, creating a new expanding universe inside. In this picture, every black hole could be a seed, a portal where one universe gives birth to another. And the Big Bang, the moment we call our beginning, may have been the result of such a bounce, the rebirth of space-time from the core of a dying star in another cosmos. It's an extraordinary possibility because it solves several long-standing puzzles at once. Why the universe expanded so smoothly and uniformly from the start. Why the total angular momentum of the cosmos seems close to zero. And why the laws of physics appear fine-tuned for stability, as if inherited from a parent world. Even the structure of a black hole's interior fits this pattern. Outside the horizon, time flows forward. Inside, space and time switch roles. To an external observer, nothing ever escapes. But to an observer inside space-time continues freely forward and expanding. If that's true, then our own universe might simply be what it looks like from the inside of someone else's black hole. And suddenly the ultimate question of cosmology changes. Instead of asking, where did the universe come from? We must ask, what universe came before ours? When you fall toward a black hole, nothing feels unusual at first. You drift through space as always until the curvature begins to dominate. The closer you get, the more the fabric of space-time bends. And then at the event horizon, something remarkable happens. Space and time trade roles. Outside the horizon, you can move freely through space, but only forward through time. Inside, that freedom disappears. Time becomes a direction you cannot choose, and that direction points inward. Falling toward the center is no longer motion through space. It's motion through time itself. Reaching the singularity is as inevitable as tomorrow. This bizarre geometry comes directly from Einstein's field equations. The solution describing a non-rotating black hole, the Schwarzschild metric, shows that near the event horizon, the sign of the space-time coordinates flips. Mathematically, the inside of a black hole isn't a place you can explore, it's a moment you must reach. But if the black hole spins, as almost all real ones do, the structure changes completely. In 1963, Roy Kerr found the rotating solution to Einstein's equations, revealing that a spinning black hole contains not one horizon, but two, and between them a region where space-time twists so violently, it can in theory connect to another universe. This isn't speculation, it's a direct consequence of relativity. Rotation drags space-time around with it, a phenomenon called frame dragging. Near a rapidly spinning black hole, this twisting becomes so strong that it creates a tunnel-like geometry known as an Einstein-Rosen bridge. While in classical physics that bridge would collapse instantly, modern quantum models suggest that the collapse might not destroy information. It could instead transform it. Here's the paradox. From the outside, nothing can ever cross the horizon. From the inside, nothing can ever stay still. Space-time itself is falling inward, carrying everything with it. It's not matter being pulled in, it's space itself flowing like a river moving faster than light toward the core. This river model of black holes proposed by Andrew Hamilton at the University of Colorado helps visualize the impossible. Outside the horizon, the flow speed is below light speed, so light can still escape. At the horizon, space falls inward exactly at light speed. Beyond it, the flow becomes faster than light, and light, no matter how hard it tries, is carried inward forever. It's not trapped because it's weak. It's trapped because the current of space itself drags it down. Inside that geometry, time doesn't end. It continues along the inward direction. And that opens a new question. If time moves inward instead of forward, what lies at the end of time's path? Is it truly a singularity, a point of infinite density, or is it the beginning of something else? That's where quantum physics enters the story, because while relativity predicts an end, quantum theory suggests a rebound, a place where gravity and matter compress to their limits and then push back, birthing something entirely new. Einstein's theory tells us what happens when gravity dominates, but it breaks down at the deepest point of collapse. At the singularity, space and time are crushed into a point of infinite density, and the equations of general relativity simply stop working. That's where quantum mechanics must take over. In the quantum world, nothing is perfectly smooth. Energy, space, and even time exist in discrete packets, quanta. At scales smaller than a trillionth of a meter, space-time itself begins to fluctuate like the surface of a boiling liquid. Physicists call this the Planck scale, and it's here that gravity and quantum physics finally meet. But these two theories, relativity and quantum mechanics, don't cooperate easily. Relativity describes the cosmos as a smooth fabric. Quantum theory sees it as granular and uncertain. Unifying them has been one of physics' greatest challenges for a century. One approach, known as loop quantum gravity, may finally offer a clue. In the 1990s, physicists Abhay Ashtekar and Carlo Rovelli developed loop quantum gravity LQG, a theory suggesting that space isn't continuous. It's woven from tiny loops of energy. Each loop is a quantum of area or volume, and the geometry of space-time emerges from their interconnections. In this picture, a singularity, a point of infinite density, can never form because there's a smallest possible unit of space. Once the density reaches that limit, gravity stops compressing and begins to repel. This is what physicists call a quantum bounce. When applied to cosmology, the same math that describes the interior of a black hole predicts that the collapsing core could rebound, expanding outward as a new separate region of space-time. From the outside, it remains a black hole, but from the inside, it looks like the birth of a universe. Space expanding, time flowing forward, energy released in all directions. This is where Nikodem Popiavski's model becomes powerful. By combining Einstein-Cartan theory with quantum spin effects, he showed that the torsion or twisting of space-time caused by particle spin can act like a spring. As matter compresses, torsion resists, preventing infinite collapse. The result is a bounce or release not into the same universe, but into a new one on the other side of the event horizon. Mathematically, it fits beautifully. A collapsing star in one universe becomes the Big Bang of another. The child universe expands, independently sealed off by the parent's horizon. Information isn't lost. It's transferred, encoded in the structure of space-time itself. And here's what makes this idea so compelling. It doesn't break physics. It doesn't require exotic matter or new forces. It simply extends the laws we already know into the quantum regime where curvature becomes discrete and gravity becomes repulsive at extreme densities. If this model is right, then the Big Bang wasn't the absolute beginning, it was a transition. A moment when a dying star's core, crushed by its own gravity, reached the quantum limit and rebounded outward, forming the expanding cosmos we now inhabit. And every black hole we see in our sky could be doing the same, silently generating new universes beyond our reach. Each collapse a rebirth, each horizon a border between realities. It's not a poetic idea, it's a physical one. A solution to the singularity problem that turns the end of space into the beginning of another. Einstein's theory tells us what happens when gravity dominates, but it breaks down at the deepest point of collapse. At the singularity, space and time are crushed into a point of infinite density, and the equations of general relativity simply stop working. That's where quantum mechanics must take over. In the quantum world, nothing is perfectly smooth. Energy, space, and even time exist in discrete packets, quanta. At scales smaller than a trillionth of a meter, space-time itself begins to fluctuate like the surface of a boiling liquid. Physicists call this the Planck scale, and it's here that gravity and quantum physics finally meet. But these two theories, relativity and quantum mechanics, don't cooperate easily. Relativity describes the cosmos as a smooth fabric. Quantum theory sees it as granular and uncertain. Unifying them has been one of physics' greatest challenges for a century. One approach, known as loop quantum gravity, may finally offer a clue. In the 1990s, physicists Abhay Ashtekar and Carlo Rovelli developed loop quantum gravity LQG, a theory suggesting that space isn't continuous. It's woven from tiny loops of energy. Each loop is a quantum of area or volume, and the geometry of space-time emerges from their interconnections. In this picture, a singularity, a point of infinite density, can never form because there's a smallest possible unit of space. Once the density reaches that limit, gravity stops compressing and begins to repel. This is what physicists call a quantum bounce. When applied to cosmology, the same math that describes the interior of a black hole predicts that the collapsing core could rebound, expanding outward as a new separate region of space-time. From the outside, it remains a black hole, but from the inside, it looks like the birth of a universe. Space expanding time, flowing forward energy released in all directions. This is where Nikodem Poplawski's model becomes powerful. By combining Einstein-Cartan theory with quantum spin effects, he showed that the torsion or twisting of space-time caused by particle spin can act like a spring. As matter compresses, torsion resists, preventing infinite collapse. The result is a bounce or release not into the same universe but into a new one on the other side of the event horizon. Mathematically, it fits beautifully. A collapsing star in one universe becomes the Big Bang of another. The child universe expands independently, sealed off by the parent's horizon. Information isn't lost, it's transferred, encoded in the structure of space-time itself. And here's what makes this idea so compelling. It doesn't break physics. It doesn't require exotic matter or new forces. It simply extends the laws we already know into the quantum regime where curvature becomes discrete and gravity becomes repulsive at extreme densities. If this model is right, then the Big Bang wasn't the absolute beginning. It was a transition. A moment when a dying star's core, crushed by its own gravity, reached the quantum limit and rebounded outward, forming the expanding cosmos we now inhabit. And every black hole we see in our sky could be doing the same, silently generating new universes beyond our reach. Each collapse a rebirth, each horizon a border between realities. It's not a poetic idea, it's a physical one, a solution to the singularity problem that turns the end of space into the beginning of another. Every scientific idea, no matter how extraordinary, must face the same test observation. If our universe was truly born inside a black hole, then that origin should have left fingerprints across the cosmos. In the way light moves, galaxies spin and matter arranges itself on the larger scales. The first clue comes from the faintest light in existence, the cosmic microwave background, or CMB. It is the relic radiation left over from the early universe, a fossil record of what space looked like when it was only 380,000 years old. If the universe had begun as a chaotic explosion, distant regions would never have been in contact long enough to equalize in temperature. Yet the CMB is astonishingly uniform, varying by less than 1 part in 100,000. Inflation theory explains this by invoking a burst of faster-than-light expansion right after the Big Bang. But a universe born inside a black hole offers a simpler alternative. Before the rebound, all matter and energy were confined within the same collapsing region. Everything was already in contact, already balanced before expansion began. That's why the early universe looks so smooth. It inherited its uniformity from the parent cosmos that collapsed before it. Another piece of the puzzle appears in the way galaxies spin. In a perfectly random universe, the rotation of galaxies should be evenly distributed, half spinning one way, half the other. But in 2020, astrophysicist Lior Shamir at Kansas State University noticed a subtle imbalance. Across immense regions of the sky, more galaxies rotated in one direction than the other. The effect is small, but statistically real. It could mean that the universe itself has a faint global rotation, a leftover twist from a parent black hole that was spinning before it gave birth to ours. That's exactly what the Kerr solution to Einstein's equations predicts. A rotating black hole imparts angular momentum to the space inside it. Our entire cosmos might be carrying that inherited spin, still written into the motion of galaxies billions of light years apart. Then came the shock from the James Webb Space Telescope. When Webb looked deeper into time than any telescope before it, astronomers expected to find small primitive galaxies struggling to form their first stars. Instead, they saw giant, massive, well-structured galaxies appearing just a few 100 million years after the supposed beginning. According to conventional cosmology, that's far too soon. There shouldn't have been enough time for gravity to assemble such complex systems. But in a black hole origin scenario, that makes sense. A universe born from a previous collapse begins already dense, already organized. The conditions needed for rapid structure formation would exist from the very start. Those impossible galaxies may not be anomalies at all. They might be evidence of a cosmos that didn't start from nothing but from something older. There's also the mystery of entropy and information. In the 1970s, Jacob Bekenstein and Stephen Hawking discovered that a black hole's entropy, its total information content, scales not with its volume but with the surface area of its horizon. That finding led to one of the most important principles in modern physics, the idea that all information inside a region of space can be described by data on its boundary. It's called the holographic principle, and it suggests that reality itself might be encoded on a cosmic surface, exactly what we'd expect if our universe were the interior of a black hole. In such a model, the three-dimensional world we experience would be the projection of information preserved on the boundary of space-time. Even direct astronomical observations point in the same direction. When LIGO detected gravitational waves from merging black holes, and when the Event Horizon Telescope captured the first image of a black hole's shadow, what they revealed matched Einstein's predictions perfectly. Yet neither experiment showed any evidence of a singularity of infinite density or destruction. Everything stops at the horizon. No one has ever seen beyond it. That might not be because nothing lies beyond, but because what's beyond becomes a separate, expanding reality of its own. Individually, each of these clues can be explained in other ways. Together, they form a pattern that is hard to ignore. The smoothness of the CMB, the directional bias in galaxies, spins the premature galaxies and Webb's images. The holographic nature of information all align with a universe that may not be infinite, but contained, curved, and inherited. It's still a hypothesis, but it's a hypothesis that fits one that ties together decades of disconnected puzzles into a single coherent story. A story in which our cosmos is not the beginning, but the continuation of something that came before. And if that's true, every black hole we see in the sky may be more than a grave of light. It may be a womb of creation holding within it the next generation of universes waiting to expand just as ours once did. In the 1970s, physicists discovered something about black holes that changed the way we think about reality itself. When a black hole absorbs matter, it should in theory trap everything forever. Nothing escapes, not even light. But according to Stephen Hawking and Jacob Bekenstein, that isn't the whole story. Their calculations showed that a black hole has entropy, a measure of how much information it contains, and that entropy doesn't depend on how much space the black hole encloses, but on the area of its surface. That single detail broke everything we thought we knew about physics. In everyday life, information scales with volume. A larger box can store more books, more air, more atoms. But a black hole doesn't follow that rule. Its total information, everything that has fallen in, is stored not throughout its volume, but on its boundary, the event horizon. Every bit of data, every particle that ever crossed that surface becomes encoded there in some microscopic form. This discovery led to one of the most profound principles in modern physics, the holographic principle. It suggests that all the information about a three-dimensional region of space can be completely described by data written on its two-dimensional surface. Just like a hologram on a flat sheet of film can project a full 3D image. The universe itself may be the projection of information stored on a cosmic boundary. Years later, this idea found a mathematical foundation. In 1997, theoretical physicist Juan Maldazzina proposed the ADS-CFT correspondence, a precise duality between two kinds of universes. On one side, there is a space with gravity in 3 dimensions. On the other, a flat world without gravity in 2 dimensions. And remarkably, both systems describe exactly the same physics. Every event happening inside the 3D space has an equivalent representation on the 2D boundary. 2 descriptions, 1 holographic reality. For the first time, the holographic principle wasn't just speculation. It was a working mathematical model. It showed that gravity and quantum mechanics, 2 seemingly incompatible theories, could coexist perfectly if space-time itself was holographic. The implications were enormous. It meant that the universe could preserve information indefinitely, that nothing is ever truly lost, only transformed or re-encoded in a deeper layer of reality. And this connects directly to the idea that our universe might be the interior of a black hole. Because a black hole already behaves holographically, its surface area, not its interior volume, determines how much information it holds. If our cosmos follows the same rule, then the 3-dimensional world we live in could be the holographic interior of a much larger, higher dimensional structure. Our stars, galaxies, and even ourselves could be patterns projected from data imprinted on a distant surface. The cosmic horizon that bounds our observable universe. This doesn't make reality an illusion. It simply means that space and matter might be emergent properties built from underlying information. The equations of relativity describe how that information curves and moves, while the laws of quantum mechanics describe how it fluctuates and evolves. Together they form a single consistent picture, a universe that encodes itself. Even experiments have begun to test this possibility. Projects such as Fermilab's holometer and the GEO 600 interferometer in Germany have searched for signs of holographic noise, tiny quantum jitters that would appear if space is built from discrete bits of information. So far the results remain inconclusive, but the limits are tightening. Each new measurement pushes us closer to answering a question once thought philosophical. Is space continuous, or is it made of information? If the holographic principle is true, it not only explains how information survives inside black holes, but also how our universe could have emerged from one. The event horizon of the parent black hole would act as the surface storing all the information of our world. Inside that surface projected by it lies everything we call the cosmos. So when we look out at the edge of the observable universe, we may not just be seeing across vast distances. We may be looking toward the very boundary where our reality is written, a horizon that holds the code of everything that exists inside. When we look out into the night sky, it feels infinite. Galaxies stretch in every direction, and no matter how far we look, there's always more. But infinity may be an illusion. The universe could be finite not because it has an edge, but because space itself curves back on itself. And if our universe was born inside a black hole, that curvature isn't just possible, it's required. In Einstein's theory of general relativity, space and time are not rigid backgrounds. They bend and flex in response to matter and energy. Add enough mass and you don't just distort space locally, you change its overall shape. A universe dense enough in matter will naturally curve inward, forming a closed geometry. In such a cosmos, if you could travel in a perfectly straight line long enough, you'd eventually return to your starting point. There are no boundaries, no walls, and no outside. Space simply loops. Over the past 2 decades, cosmologists have tried to measure the shape of the universe with extraordinary precision. They've done this by mapping the cosmic microwave background, the faint afterglow left from the early universe. The subtle patterns in that light reveal how space bends on the larger scales. If the universe were open, those ripples would appear smaller. If it were closed, slightly larger. The latest data from the Planck satellite show a geometry that is almost perfectly flat, but not entirely. A slight positive curvature remains possible, suggesting that the universe could indeed be closed, wrapping back on itself far beyond our observable horizon. This fits beautifully with what we would expect inside a black hole. A black hole's interior is a region of space-time with strong positive curvature, a space that folds inward. If our cosmos occupies that interior, its overall geometry should reflect that curvature. From our perspective, it would seem endless because the curvature is gentle across billions of light years. But in reality, it would be finite, contained within the horizon of the parent black hole. Some researchers have even pointed out small hints that support this possibility. In 2019, a reanalysis of Planck data suggested the universe might have a slightly higher density than expected, a sign of closed curvature. It's not yet conclusive, but it's a tantalizing clue. If confirmed, it would mean that the cosmos doesn't stretch infinitely in every direction, but instead forms a gigantic curved bubble, a self-contained volume of space-time expanding from within. And that curvature doesn't just describe the shape of space, it also defines the flow of time. In a closed universe, gravity and geometry are linked so tightly that the entire system could one day reverse its expansion and collapse again. In that moment, every black hole that forms within it could repeat the process, each one a seed for a new curved region of space-time beyond its own horizon. When seen this way, the universe resembles a vast geometric cycle, each collapse leading to new expansion, each interior forming its own self-contained cosmos. The curvature of our space, faint but measurable, could be the trace of that deeper connection. It's the geometric echo of the black hole that came before. So when astronomers say the universe appears flat, it doesn't mean it truly is. It only means that our cosmic neighbourhood is too small a window to reveal the full curve. If we could somehow step back far enough beyond the reach of light, we might see the universe for what it really is. A a curved finite bubble of space-time closed upon itself, expanding within the unseen geometry of a large reality. And in that case, the illusion of infinity would simply be our limited perspective, the view from inside a cosmic sphere growing within the heart of a black hole. When something falls into a black hole, it seems to vanish forever. A star, a planet, or even light itself all disappear beyond the horizon, leaving nothing behind. From the outside, it looks like the perfect destroyer, erasing not just matter, but the very information that once defined it. And that is a problem, because in quantum physics, information can never be lost. Every process in the universe, from the decay of an atom to the collision of galaxies, must conserve information. Even when energy changes form or matter transforms, the quantum data describing those changes remain encoded in the system. If black holes truly erase information, they would break one of the most fundamental laws of physics. This paradox haunted Stephen Hawking for decades. In the 1970s, Hawking made a revolutionary prediction. Black holes aren't completely black. They emit faint radiation, now called Hawking radiation, produced by quantum effects at the event horizon. Pairs of virtual particles constantly pop in and out of existence in empty space. If one of those particles falls into the black hole while the other escapes, the escaping particle carries away a tiny amount of energy. Over immense timescales, that process causes the black hole to lose mass and eventually evaporate. But that only deepened the mystery. If a black hole can vanish, taking all the matter it absorbed with it, where does the information go? If it's truly gone, then the laws of quantum mechanics fail. If it somehow survives, then where is it stored? Decades of research led to a remarkable realization. The information might never have been inside the black hole at all. It could have been stored on its surface, encoded in microscopic patterns on the event horizon itself. This idea, developed by physicists like Gerard 't Hooft and Leonard Susskind, eventually led to the holographic principle. Everything that happens inside a region of space can be described by data on its boundary. In this view, a black hole is not a void, but a kind of quantum memory device. Its surface area measures how much information it holds. Every particle that falls in changes that surface, slightly altering its microscopic configuration. The interior, we imagine the bottomless pit of gravity, is actually a holographic projection of that information encoded on the horizon. Nothing is lost. It's simply transformed into a different language of physics. Over time, the escaping Hawking radiation carries that information back into the universe. At first it seems random, like static noise, but deep within the equations of quantum mechanics there are correlations patterns that in principle could reconstruct everything that ever fell in other words, the black hole doesn't destroy information, it scrambles it like a cosmic encryption system. If that's true, then our universe, if it formed inside a black hole, could follow the same rule. All the information about everything we see from atoms to galaxies would be encoded on a larger boundary, the event horizon of the parent black hole. Our cosmos would exist as the internal projection of that data, evolving naturally according to the same quantum laws. From the outside, information falls in. From the inside, that same information expands outward as a new universe. Even the evaporation process itself could explain the life cycle of universes. As the parent black hole loses energy through Hawking radiation, the universe within it could experience cosmic acceleration, what we observe as dark energy. The geometry connects. The slow decay of the horizon outside could appear as an accelerated expansion inside. To the physicists who study these questions, this isn't speculation. It's the only way the mathematics make sense. Quantum theory insists that reality must conserve information, and if the universe behaves holographically as the evidence increasingly suggests, then no information is ever truly lost. It is always preserved on a surface in a field or across the horizon of something larger, so perhaps our universe's own horizon. The edge of the observable cosmos is performing the same function. It holds in microscopic form the complete quantum record of everything that has ever happened within, and somewhere beyond that boundary in dimensions we cannot reach, the parent reality continues to exist its own information written across the horizon that once gave birth to us. In the end, the black hole paradox may not be a paradox at all. It may be a clue, a quiet reminder that what seems to disappear never truly does. Information, like the universe itself, only changes form. It folds, expands, and encodes itself in ways we are just beginning to understand. And in that transformation, it might carry the secret of where we came from and where we're heading next. When we look into deep space, we're also looking into the past. Every light that reaches us has travelled for billions of years, crossing a universe that has been expanding the entire time. The farther we look, the older the light, until we reach the limit, a glowing wall of radiation known as the cosmic microwave background. Beyond that, there is no visible past, not because nothing exists there, but because light itself has not had enough time to reach us. That invisible boundary is called the cosmic horizon, the farthest distance any information can ever travel in the age of our universe. If our cosmos truly lies inside a black hole, this horizon might be more than just a limit of observation. It could be the literal event horizon of the parent black hole, the surface that defines the boundary between two realities. Everything we see, from the smallest particle to the largest galaxy, would exist within that boundary, expanding in time while remaining sealed in space. But how could we ever know? If we are inside, then by definition nothing from beyond that horizon could reach us. We cannot step outside to look back in. The only way to test the idea is to study the subtle traces that the boundary might leave on the physics we can observe. One of the first places to look is the cosmic microwave background itself. It's not perfectly uniform. It carries faint anisotropies, tiny variations in temperature and polarization. Some of those patterns, like the mysterious cold spot and the large-scale alignment known as the axis of evil, have puzzled cosmologists for years. They stretch across regions too vast to be explained by local effects. Some researchers have proposed that they might be signs of boundary conditions, imprints from the edge of a closed, curved space. If the universe has a horizon that defines its geometry, that horizon could leave subtle echoes frozen in the CMB waiting for us to decode them. Another clue may come from the accelerating expansion of the cosmos. Distant galaxies aren't just moving away, they're speeding up, carried by an unknown force we call dark energy. In a universe inside a black hole, this acceleration could be a geometric illusion. From the inside, expansion looks like space stretching faster and faster. From the outside, it would be the slow evaporation of the parent black hole through Hawking radiation. What we interpret as dark energy could simply be the inside view of that process, the gradual loss of mass beyond our cosmic horizon. There are also limits to what we can ever see, no matter how advanced our technology becomes. The expansion of space itself means that regions of the universe are receding faster than light. Beyond about 46 billion light years, light will never reach us no matter how long we wait. That distance defines a kind of observational prison, not because of walls, but because of the nature of space-time. It's a silent confirmation of what Einstein's geometry already tells us. We live inside a self-contained bubble of reality defined by its own horizon. Still, scientists continue to search for ways to probe that edge indirectly. Upcoming missions like Lightbird and the CMB-S4 experiment will map the polarization of ancient light with unprecedented precision, looking for the faint fingerprints of curvature or boundary physics. Gravitational wave detectors may someday sense ripples that interact with the fabric of space-time itself, offering hints of structures beyond the visible horizon. If the universe truly curves back on itself, those signals might betray its hidden shape. But perhaps the most profound evidence is conceptual. Every law of physics we know, from relativity to quantum mechanics, works perfectly inside a bounded system. None of them require infinite space. What they describe is self-contained, finite, and complete. That may be the greatest hint of all. The universe behaves as if it were inside something, as if there's an unseen boundary that defines where information can go and what it can do. And maybe that's the reason we can never find the edge, because the edge is not a place in space. It's a limit in time, in causality, and what light can reveal. The universe may not end in a wall of matter or a void of darkness, but in the boundary of knowledge itself, the horizon beyond which there is only silence. If our universe was born inside a black hole, then that silence isn't emptiness. It's the surface of another world, a frontier that gave birth to ours. And as we stare deeper into the cosmos, into light that has travelled for almost 14 billion years, we may already be seeing the reflection of that boundary, the shimmering edge of the horizon that made everything possible. Every time a massive star dies, it collapses under its own gravity. Its core implodes, crushing atoms, breaking matter into its most fundamental pieces and forming a black hole, a point of no return. But what if that collapse isn't the end? What if inside each of those black holes a new universe is born, expanding, evolving and creating its own stars, its own galaxies, its own laws of physics? This idea, once dismissed as pure speculation, is now being taken seriously by some of the world's leading cosmologists, because when the equations of relativity are pushed to their limits, they don't stop at the event horizon. They continue describing a region of space-time that expands rather than collapses. To an observer outside, everything falls inward. To an observer inside, everything moves outward. The singularity that seems to end one universe may from the inside look like the Big Bang of another. Physicist Nikodym Popławski has suggested exactly that. Every black hole could be a gateway to a new universe connected to its parent through a one-way bridge of space-time. The spin of particles and the torsion of space prevent a total collapse, creating a bounce, the rebirth of expansion from within. Each universe in turn forms its own stars, its own black holes, and its own offspring. Reality then may not be a single cosmic stage, but a branching network of universes, each one born from the death of another. If that's true, then the structure of existence could be fractal, self-replicating across unimaginable scales. From the smallest quantum fluctuations to the vastest galaxies, the same principle might repeat. Collapse and rebirth, contraction and expansion, information preserved and re-expressed. The Big Bang would not be unique. It would be one of countless beginnings, each taking place inside the event horizon of a dying world. This model could even explain one of the greatest mysteries in physics: why the laws of our universe seem perfectly tuned for stability and complexity. If universes are born through black holes, each with slightly different physical constants, then only the ones with the right balance, where stars can form, where matter can clump, where atoms are stable, would continue to evolve and create new black holes of their own. Over cosmic timescales, this becomes a kind of cosmological natural selection. Universes that produce more black holes give rise to more offspring. The cycle favours those with the right ingredients for long-term structure universes like ours. This doesn't require design or coincidence. It's simply the mathematics of survival extended to the scale of space-time itself. A black hole is the universe's most efficient way of recycling matter and energy, and perhaps of passing on its own blueprint. In this grand perspective, every black hole we observe could be a seed, a portal not to destruction but to creation. If this chain of cosmic reproduction has no beginning and no end, then our universe is both descendant and ancestor. The black holes scattered across our galaxies are not isolated monsters, but links in an endless chain, each one holding a new cosmos within each one born from a collapse that came before. Even the distribution of galaxies hints at this fractal order. The large-scale structure of the universe, the vast filaments and voids that form the cosmic web, look strikingly similar to the magnetic and gravitational patterns seen around black holes. The same geometry repeats itself at every level, as though the universe is a scaled reflection of its own inner workings. If we could somehow step outside our universe and look down upon it, we might see it for what it truly is. One sphere among countless others, nested like bubbles within, bubbles expanding and colliding in an endless sea of creation. Each horizon a boundary between realities, each collapse the birth cry of a new world. And so the question of origin transforms. Instead of asking where the universe began, we ask how deep the chain goes. Is there a first universe? Or has the process been repeating forever, without beginning, without end, a self-replicating pattern of space and time? Perhaps even now, inside the black holes scattered across our own galaxy, new universes are unfolding, silent, unreachable, but real. And someday, the black holes born within those worlds may give rise to others still extending the pattern outward into infinity. In that vision, the cosmos is not a single story, but an eternal network, a fractal of creation, where every end is a beginning and every horizon hides another universe beyond. If our universe was born inside a black hole, then somewhere beyond our cosmic horizon lies the universe that created us, a parent world vast beyond imagination, whose dying star collapsed and gave birth to everything we know. It's a strange thought, that the galaxies, the laws of physics, even the flow of time itself could be the byproduct of a stellar death in another reality. We can't see this parent universe directly. Its event horizon isolates us completely, but physics allows us to infer what it might be like. In the Einstein Cartan model proposed by Nikodym Popławski, when matter collapses into a black hole, it doesn't reach infinite density. Instead, the spin of particles twists space-time just enough to prevent total collapse, creating a rebound, the birth of a new expanding cosmos. That new universe ours would then be hidden behind the parent's event horizon, invisible to anything outside. To an external observer, the black hole simply sits in space consuming matter. To us inside, it feels like the universe expanding in all directions. So what would that parent universe look like? It would likely resemble our own in many ways, filled with galaxies, stars and dark matter, but operating on a vastly different scale. The black hole that formed our cosmos might have originated from the collapse of a supermassive star or even the core of a galaxy. If so, the parent universe could be billions of times larger and older than ours, its black holes constantly spawning new baby universes within them, each governed by its own version of physical constants. Physicists sometimes describe this hierarchy as a cosmic tree branching endlessly upward. Each universe gives rise to smaller ones through its black holes, and those offspring in turn create their own. It's an elegant, self-perpetuating structure, one that could exist indefinitely without a single moment of true creation. There's no need for a singular beginning of time. Every universe is both child and ancestor, each horizon a gateway between generations of reality. In this picture, our own Big Bang wasn't the first nor the last. It was simply a local event, the moment when the interior of a collapsing object in the parent universe rebounded into expansion. To us, that event looks like the birth of everything. To them, it was just another star dying, disappearing into the dark. If this is true, then our universe inherits its physical constants: the speed of light, the strength of gravity, the charge of the electron from the conditions inside that parent black hole. But there's room for variation. Each new universe could differ slightly depending on how its black hole formed, and how much angular momentum or energy it contained. Over countless generations, this would create a vast diversity of universes, each with its own version of physics. Some might collapse quickly, others might never form stars. Only a few would achieve the delicate balance that allows matter chemistry and life to exist universes capable of producing black holes of their own. And so, in a sense, our parent universe is responsible not just for our space and time, but for the very conditions that make us possible. We are built from its geometry, its gravity, its fundamental code. Our galaxies carry its momentum, our atoms echo its curvature, and our physics may be the inherited language of its space-time. The question, of course, is whether we could ever detect its presence. If the boundary between our universe and the parent one is truly an event horizon, then no information can cross it directly. Yet the laws of quantum mechanics hint that there may be subtler connections through entanglement, through fluctuations at the edge of space, through the holographic imprint of our boundary. Some physicists even propose that the quantum entanglement we observe across the cosmos could be the faint residue of links to the higher dimensional geometry that surrounds us, a whisper from the universe that came before. We may never see that world with telescopes or detectors. It exists beyond the reach of light, beyond the reach of time as we know it. But in every direction we look, in the smoothness of the cosmic microwave background, in the uniformity of expansion, in the subtle harmony of the laws that govern matter, we can sense its fingerprints. We are not separate from it. We are its continuation. So when we stare into the black holes of our own universe, watching them consume the light of stars, we may be witnessing the same process that once gave rise to us. Each of those dark spheres could be the seed of another cosmos waiting quietly in the fabric of space-time, preparing to expand into its own reality. And somewhere far beyond the horizon we can never cross another universe might already be watching its own black holes, unaware that inside one of them we exist. Every beginning carries the seed of an ending, and every ending perhaps the seed of another beginning. Our universe, vast, radiant, alive with stars and galaxies, is not exempt from that rule. It too is mortal. But its death may not be the end. It may simply be the moment when the child becomes the parent. Right now, our cosmos is expanding its galaxies, drifting apart at ever-increasing speeds. Stars are burning their fuel, creating heavy elements in their cores, then dying in supernova explosions that scatter those elements into space. Over billions of years, this process has built everything planets, life, even consciousness. But it cannot last forever. The stars will fade. The galaxies will dim. And one day the night sky itself will go dark. Astrophysicists call this the heat death, the final era, when all energy becomes evenly distributed and no more work can be done. But before that distant silence arrives, something else will take over. The black holes. They will outlast everything, the stars, the planets, even the atoms themselves. As matter collapses, black holes will merge and grow, consuming the remnants of the universe one by one, until almost all mass and energy are locked within them. To an outside observer, this might look like the slow decay of the cosmos, a drift toward nothingness. But if the black hole origin model is correct, this is not decay at all. It's gestation. Inside those event horizons, new universes could already be forming, each one expanding in its own space, each one hidden beyond the boundaries of our perception. In this view, the end of our universe is also its replication. Every collapse plants the seed of a new Big Bang. The physics supports the possibility. According to the Einstein Cartan theory, when matter inside a black hole is compressed to extreme densities, the spin of particles creates a torsion, a twist in space-time that halts collapse and triggers expansion on the other side. That expansion is what we perceive as the birth of a new cosmos. If so, the life cycle of universes is not linear but cyclical, an eternal chain of rebirths, each universe giving rise to the next through its own black holes. The timeline for this transformation is almost beyond comprehension. In 10 trillion years, the last stars will burn out. In 100 trillion, the galaxies will be cold and silent. After a Google years, a number with 1 followed by 100 zeros, even black holes will begin to evaporate through Hawking radiation, releasing their mass as faint whispers of light. But during all those eons before their final fade, they may have already produced countless new universes, each expanding in its own dimension of time. Our universe then is not dying but transforming. Its energy is not vanishing but redistributing into new realities. In a sense, the cosmos is the ultimate recycler, turning collapse into creation and decay into genesis. The very black holes that seem to swallow everything could be the wombs of new universes, each carrying the legacy of the one before. If that's true, then time itself may be an infinite continuum of generations. The laws of physics we observe could be the genetic code passed down from cosmic ancestors. Each universe inherits the traits that allow it to thrive the balance between gravity and expansion, between matter and energy, while introducing small variations that shape its destiny. We are quite literally the descendants of a universe that came before and the ancestors of universes yet to come. One day, trillions of years from now, when the last black holes of our universe collapse, the cycle will continue. From the outside, our cosmos will seem to vanish into nothing. From the inside, it will begin again, a new Big Bang, a new expansion, a new tapestry of stars. The universe will not end in darkness, but in light reborn. And somewhere deep within one of those newborn worlds, intelligent beings may look out at their own sky, wondering just as we do now where their universe came from, unaware that the answer lies in the ashes of ours. If every black hole creates a universe, and every universe gives birth to more black holes, then existence itself may be infinite, not in size, but in generation. A self-replicating chain of cosmoses, each one arising from the collapse of the last, each carrying forward the information, the laws, and the possibilities of those that came before. In this vision, there is no first universe, no single act of creation. There is only continuity, a rhythm of collapse and rebirth that has no beginning and no end. The Big Bang was not a singular moment in time, but one note in an eternal symphony, the echo of countless explosions that have happened before and will happen again. We are living inside a single verse of that infinite song. Every law of physics, we know the strength of gravity, the charge of an electron, the curvature of space-time may have been inherited, passed down like genetic code from a parent universe that once existed. Slight changes in the code could produce new variations, new universes with slightly different constants, some unstable, others long-lived. Ours just happens to be one that sustains stars' matter and life long enough to wonder where it came from. If that's true, then even our curiosity is part of the pattern consciousness arising within a universe that itself was born from one before it. On the larger scales, this structure would look like a vast cosmic fractal, universes nested within universes, each connected by black holes. Portals of creation disguised as voids of destruction. From the outside, a black hole marks an ending. From the inside, it's a beginning. To the external universe, it is silent and still. To the interior, it is expanding, vibrant and alive. Reality folds back upon itself endlessly, creating, endlessly transforming. Even the flow of time might be cyclical within this framework. Each universe has its own timeline, beginning with expansion and ending in collapse. But all of them coexist within a higher dimensional reality, where time itself may be infinite. In that space there is no before or after, only the constant exchange of information, one horizon giving birth to another one, cosmos giving way to the next. Information never dies. It simply changes form, woven through the geometry of space-time like the threads of an eternal fabric. From our perspective, trapped inside this particular bubble of reality, the chain is invisible. We see only one link, our own universe, and mistake it for the whole. But the physics tells another story. The symmetry of the equations, the conservation of information, the holographic structure of space-time all hint at something larger, something unending. Perhaps the universe doesn't need an origin because it is its own origin, a loop of creation that sustains itself through the laws it generates. And if we could somehow step outside this cosmos beyond our horizon and look down upon the chain, we might see it as a boundless lattice of light and shadow, expansion and collapse, each node a universe, each connection a black hole, each horizon a border between realities. It would stretch not through space but through existence itself, a fractal of being repeating forever. Somewhere within that infinite structure lies our universe, young by cosmic standards, alive with stars rich with potential. And somewhere within ours, new universes are already being born, hidden inside the black holes we've only begun to understand. Each will inherit a piece of our physics, a reflection of our geometry, a memory of our light. This is the ultimate cosmic continuity. Matter turning into energy, energy into information, information into new universes. Creation and destruction are not opposites, but partners, the twin motions of the same eternal process. Perhaps in the end the question, where did it all begin, has no meaning, because there was never a single beginning, only transformation. An infinite cascade of horizons, each one giving birth to the next. And somewhere deep inside one of them a new universe is already awakening, filling with light stars and life wondering, just as we do now, how it all began. For 13 billion years the universe has expanded, cooled and evolved, forming stars, galaxies and worlds capable of asking questions. Now those questions point back toward the very structure that made us possible. If the cosmos is truly a black hole, a self-contained region of space that creates its own interior reality, then we are not simply observers in it. We are part of its architecture. Every atom in our bodies, every spark of thought, every photon that touches our eyes is a ripple in the same fabric of space-time that curves and folds to create the universe itself. For centuries, humans believed we stood at the center of creation. Then we learned that Earth was just one planet among many circling an ordinary star in an ordinary galaxy among hundreds of billions. And now physics suggests an even deeper shift, that the entire cosmos may itself be the interior of something larger, invisible and unreachable. We are not outside observers of the universe. We are patterns within it, coded into its geometry like notes in a symphony that plays itself. What does that mean for us? It means that our existence is not separate from the laws that shape space and time. When you move your hand through the air, you're bending space-time. When your brain thinks it's processing the same information that defines the structure of the cosmos, you are not a visitor inside reality, you are reality localized in a particular form. That realization changes how we see the universe. Instead of an empty void filled with cold stars, it becomes something dynamic. Living self-aware, a network of information, curvature and energy constantly transforming itself. The laws of physics are not distant rules written elsewhere. They are the habits of the universe, the way its fabric behaves. We are those habits, momentarily conscious of themselves. It also reframes the question of significance. If the universe is infinite in generation, with countless worlds born inside black holes, then on one scale our existence seems unimaginably small. But on another it becomes profound, because out of that endless cycle of creation and collapse, the universe has at least once produced beings capable of looking back and understanding it. That's what consciousness is, the universe examining its own interior, reflecting on its own origin. When astronomers map the cosmic microwave background or measure the spin of galaxies, they are not studying something foreign. They are uncovering the structure that gives rise to their own existence. Every equation written on a chalkboard is the universe writing to itself through the mind of a creature made from its own particles. This is what it means to live inside a black hole, not to be trapped, but to belong. To exist within a self-contained system where everything from the birth of stars to the motion of thought is part of one coherent story. A story that has been unfolding for billions of years, written in light and gravity, and now finally in words and understanding. Perhaps that is the real gift of science. Not certainty, but awareness. A reminder that we are both the observer and the observed, that every discovery about the universe is also a discovery about ourselves, and that even if we can never cross the horizon, we can still illuminate everything within it. Because the deeper we look into the universe, the more it reveals that we were never apart from it. We are its expressions, its memory, its question and its answer all at once. When Albert Einstein published his general theory of relativity in 1915, he changed not just physics, he changed the way reality itself was understood. Before him, space was thought to be a stage in time, a ticking clock that measured events as they unfolded upon it. After Einstein, the stage and the clock disappeared. What replaced them was something unified space-time, a single fabric that bends, twists and stretches under the influence of matter and energy. Everything that exists, the Earth, the Sun, the Milky Way, sits on this invisible fabric. When mass is present, it doesn't merely pull on other mass, it warps the fabric around it. Planets don't orbit the Sun because of a mysterious force pulling them inward. They move the way they do because space itself curves around the Sun, guiding them along paths called geodesics, the straightest possible lines through a curved reality. Imagine placing a heavy ball on a stretched rubber sheet. The sheet dips and a smaller ball rolling nearby will spiral around it. That's the geometry of gravity, not a force acting at a distance, but the motion of objects following the curves of space-time. This simple idea explained everything Newton's equations couldn't. The precession of Mercury's orbit, the bending of starlight near the Sun, and the dilation of time itself near massive bodies. But space-time isn't static, it flows. Einstein's equations describe it as a dynamic field stretching where matter moves apart, rippling when energy changes, and collapsing when mass becomes dense enough. Even light, the fastest thing in the universe, is not immune to this flow. Its path bends around galaxies, forming arcs and rings, gravitational lenses, as if the cosmos itself were made of glass. Physicists have a way to picture this behaviour, the river model of space-time. Imagine space as a river flowing toward the centre of a black hole. Far from the hole, the current is slow, light can still swim upstream. Closer in the flow, speeds up until at the event, horizon space itself falls inward at the speed of light. Beyond that, the current moves faster than light can escape, carrying everything with it toward the core. What falls into a black hole isn't just matter, it's space itself flowing like water down a cosmic drain. This same concept applies on a universal scale. The expansion of the universe isn't galaxies flying apart through space, it's space itself stretching between them. Light doesn't move through a pre-existing void. The void is what's moving. Distances grow, not because things are travelling outward, but because the metric that defines those distances is changing. Space and time are not containers, they are the content. And like any fabric, space-time can vibrate. When massive objects such as black holes or neutron stars collide, they send ripples across the cosmos, gravitational waves. These are not waves in space, they are waves of space. They carry information about cataclysmic events, billions of light years away, compressing and stretching reality itself as they pass through us. We don't just observe the universe, we feel it moving through us. That motion is not metaphorical. Every point in space is part of a larger flow woven into a geometry that responds instantly to the presence of energy. And because energy and mass are equivalent E equals mc squared, every action, every photon, every thought alters that geometry in some microscopic way. Reality in its purest form is a dynamic network of curves, flows and vibrations, a living responsive fabric. The more we learn about it, the stranger it becomes. Space can expand faster than light without breaking any laws. Time can slow to a crawl near a black hole and stretch infinitely from another point of view. These effects aren't illusions or distortions, they are the shape of reality itself. We live not in a rigid universe, but in one that moves, flexes, and evolves. When we say the universe might exist inside a black hole, this is what we mean. We're not talking about a hole in space, but a region of space-time that has folded upon itself. A geometry that curves so completely it becomes its own self-contained world. Everything we know, every measurement we make is part of that curvature. Space and time are not the backdrop to existence. They are existence. And like any fabric, they may someday tear or rebound or give birth to something new. Because in the end, the universe doesn't just contain structure, it is structure. a flowing self-aware geometry, and we are the patterns written into its folds. We live our lives in one direction. The past becomes memory. The future remains unknown, and the present slips away the moment we notice it. But in physics, that sense of flow of one moment becoming another might be an illusion. Time as we experience it may not be something the universe has. It may be something the universe creates. In Einstein, space-time time is not a universal rhythm ticking everywhere at once. It is woven together with space, forming a single four-dimensional structure. Every event, every explosion of a star, every heartbeat, every photon emitted from a distant galaxy already has a coordinate in that structure. Past, present, and future all coexist within it. This is the block universe where time is not something that flows, but something that is. Nothing moves through time. Instead, time is simply another dimension we inhabit, like depth or height. From that perspective, the flow of time we perceive is not a feature of the universe. It's a feature of our perception. Our brains evolved to record change, to compare states, to distinguish before from after. The universe itself may not be changing at all. What we call change might just be the way we move through space-time's geometry, tracing a particular path among all possible events. Yet there's something undeniably special about time's direction. Entropy, the measure of disorder, always increases. A glass shatters, but the shards never reassemble. A star burns its fuel, but never spontaneously reignites. This arrow of time is what separates yesterday from tomorrow, and it's not written into the equations of physics. The fundamental laws, gravity, electromagnetism, quantum mechanics, work perfectly well both forward and backward. So why does time move only one way? The answer lies in probability and information. When the universe began, it was in a state of astonishing order. A smooth, dense plasma with extremely low entropy. As it expanded, that order broke down. Structures formed, stars ignited, life emerged. Every step added complexity, but also increased entropy. What we perceive as the passage of time is the accumulation of that change. The universe unfolding from simplicity to diversity, from low entropy to high. In other words, time might be emergent, not a fundamental ingredient, but a byproduct of the universe's tendency toward disorder. Without change, without entropy, there would be no before and after. A universe in perfect equilibrium would be timeless, frozen, static, eternal. At the quantum level, the concept of time becomes even more elusive. In the equations of quantum gravity, time often disappears entirely. The most basic equation in that framework, the Wheeler-DeWitt equation, has no time variable at all. It describes a universe that simply is not one that happens. To get time back, physicists have to introduce interactions, relationships between quantum systems. Time emerges only when one part of the universe can act as a clock for another. In that sense, time is relational, a measurement of change between two correlated systems. This view aligns with work by physicists like Julian Barber, who argues that what we call time is really just the difference between configurations of the universe. Each configuration, each now, is a snapshot of geometry and matter. The sequence of these snapshots creates the illusion of flow. But all of them, past and future alike, coexist timelessly in the landscape of possibility. Even in our daily lives, we see hints of this. At high speeds or near massive objects, time dilates, it slows. Clocks tick differently depending on their motion and position in a gravitational field. That means time is not absolute. It's flexible, local, subjective. The rhythm of the universe is felt from a particular place and velocity. It's not the universe moving forward. It's us moving through the universe's geometry. If time is emergent, then so is change. The Big Bang didn't start time, it defined one end of it. And when the universe eventually reaches thermal equilibrium, when entropy stops increasing time as we know it may cease to exist, the cosmos will still be, but it will no longer become. And yet this doesn't make our experience of time meaningless. It makes it extraordinary. Because within the geometry of space-time, we conscious beings made of matter and light experience the one thing the universe itself doesn't, the feeling of motion through eternity. We give the universe a sense of now transforming its static existence into a living story. Perhaps that's the paradox of being alive in a timeless cosmos. The universe may not need time, but we do. We are how it remembers that it's still unfolding. Every night we look up and see the universe stretching before us. Galaxies drifting apart, the cosmic web thinning like red-shifting as it travels through the void. We know the universe is expanding, but there's a question that feels impossible to ignore. If space is expanding, what is it expanding into? What lies outside the universe? It's a natural question, one that seems obvious until physics reveals just how strange the answer is. Because according to everything we know about space-time, the universe isn't expanding into anything. Space itself is what's growing. There is no outside, no cosmic air, no background void waiting to be filled. The expansion of the universe is not like a balloon inflating into surrounding air. It's more like the surface of the balloon itself, a two-dimensional skin stretching where every point moves away from every other. But there's no edge to move toward. This idea comes from Einstein's equations, which describe how distances between points in space-time change over time, not because objects are flying through space, but because space itself is stretching. This is what cosmologists call metric expansion. It means that the coordinate system we use to measure distance is itself changing. In other words, galaxies are not moving through space. The space between them is increasing. Even light travelling at the ultimate cosmic speed limit cannot keep up with that stretching on large enough scales. Imagine dots drawn on a balloon. As the balloon inflates, each dot sees every other dot moving away. From any one point, it seems as though you're at the centre of the expansion, but there is no centre. The balloon's surface doesn't expand into something else, it simply becomes larger. Now extend that idea to 3 dimensions. That's our universe. A self-contained geometry that expands without needing an external space. This also means the universe doesn't have an edge, not in the way we imagine it. You can't reach the end of space and step into something beyond. If you could travel far enough in one direction, ignoring the fact that cosmic expansion would outpace you, you might eventually curve back around to where you started, just as a traveller circling the globe returns to the same spot. That's because our universe could be finite but unbounded, like the surface of a sphere in higher dimensions. It's complete in itself. So if there's no outside, how do we visualize this expansion? Think of the fabric of space-time from before a flexible dynamic medium. When matter and energy exist within it, they determine how it curves. But on cosmic scales, something else dominates. Dark energy, a mysterious pressure embedded in the vacuum itself. Dark energy pushes space-time to expand faster and faster. It's not space moving into anything, it's more like the metric that defines distance between galaxies is being rescaled over time. The ruler of the universe keeps stretching. Here's the mind-bending part. Because of this expansion, galaxies far enough away are receding from us faster than the speed of light. Not because they're moving faster than light, but because the space between us is expanding. Their light will never reach us. Each second more of the universe slips beyond what we can ever see, crossing our cosmic event horizon forever out of reach. That horizon defines the limit of our observable universe. About 46 billion light years in every direction. Beyond it there may be infinite galaxies, but we'll never know. They are in a very real sense outside our observable reality, though not outside the universe itself. This idea becomes even more profound when linked to the black hole model we discussed earlier. Inside a black hole, space-time also stretches but inward toward a singularity. In our universe, space-time stretches outward away from the initial condition we call the Big Bang. Both obey the same geometry but viewed from opposite sides of the same equation. It's possible that what we perceive as the expansion of our universe is simply the interior growth of a black hole's space-time bubble in another universe. Inside, we see galaxies receding. Outside, an observer would see matter collapsing. So what is space expanding into? It's expanding into itself. Each new region of space-time that forms is not invading a pre-existing void. It is creating more reality. Expansion doesn't require a destination. It only requires the mathematics of curvature and energy density. The universe is not a ship sailing into an ocean. It is the ocean making more ocean as it flows. Perhaps the deeper question is not what is it expanding into, but why is it expanding at all? And that in turn might point back to its origin, whether the expansion we see is the aftershock of a cosmic bounce, or the natural unfolding of a space-time born inside a black hole. Either way, the conclusion remains stunning. Our universe is not moving through anything. It's moving as itself. The stage and the play are one and the same, a living expanding geometry that creates its own arena as it evolves. When you look into the night sky and see distant galaxies drifting apart, you're not watching motion through space. You're witnessing the universe growing not into emptiness but into being. At the end of the 20th century, astronomers made one of the most shocking discoveries in all of science. They expected the universe's expansion to be slowing down the mutual gravity of billions of galaxies, pulling everything back together. But when they measured distant supernovae, they found the opposite. The universe isn't just expanding, it's expanding faster and faster. Something invisible, uniform and powerful is pushing the cosmos apart. They called it dark energy. We still don't know what dark energy is. It makes up roughly 70% of everything that exists, yet it emits no light, creates no heat, and leaves no trace except in the motion of galaxies. It doesn't clump like matter or ripple like radiation. It behaves as if space itself contains a built-in pressure, an energy of the vacuum that grows stronger as the universe grows larger. This strange behavior is encoded in Einstein's own equations. When he first formulated general relativity, he noticed that the geometry of space-time could include a constant, a kind of baseline curvature that existed even in the absence of matter. He called it the cosmological constant, denoted by the Greek letter lambda L. Einstein introduced it to make the universe static, believing incorrectly that the cosmos must be eternal and unchanging. When the expansion was later discovered, he abandoned it, calling it my greatest blunder. But decades later, that same constant returned now as the simplest explanation for dark energy. In the standard model of cosmology, lambda represents a constant vacuum energy that fills all of space, causing it to expand at an accelerating rate. But the deeper question remains, why does the vacuum have energy at all? And where does that energy come from? Quantum physics tells us that even empty space isn't truly empty. It seethes with virtual particles, fleeting pairs of matter and antimatter that appear and vanish in an instant. This quantum foam gives the vacuum a measurable energy density, but when physicists calculate it, the result is off by a staggering factor, 10 to the power of 120, the worst mismatch between theory and observation in the history of science. Something fundamental is missing. One possibility is that dark energy isn't just a property of our universe. It's a sign of interaction with something beyond it. If our universe was born inside a black hole, then its boundary, the event horizon, might not be perfectly sealed. Quantum fluctuations at that surface could leak energy across it, influencing the expansion inside. In that case, what we perceive as dark energy might be the residual pull of the parent universe's gravity, acting across the boundary of space-time. Physicists like Nietzsche, Afshordi and Paul Wesson have proposed versions of this idea, that our cosmos could be the interior of a higher dimensional black hole, and its accelerating expansion is a natural consequence of the curvature imposed by the larger space beyond. In such models, the vacuum energy we observe isn't an arbitrary constant. It's geometric, arising from the way our universe's horizon interacts with the space outside it. If this is true, then the rate of cosmic acceleration could tell us something about the environment of our parent universe. A strong curvature outside could produce a faster expansion inside. In other words, dark energy might not be in the universe. It might be the shadow of the universe that contains us. Even without invoking other dimensions, dark energy reveals something profound. The vacuum itself has structure. When space expands, new vacuum forms, carrying with it the same energy density. This means that as the universe grows, it gains energy without drawing from anywhere. It's as though space-time is a self-fueling engine powered by the geometry of its own existence. That's not a violation of physics. It's built into the mathematics of general relativity. The total energy of the universe can still sum to zero, balancing positive energy in matter and radiation with the negative energy of gravity. But locally, space behaves as if it's alive, capable of stretching itself without limit. The accelerating expansion has a cost. Over billions of years, it will isolate galaxies from one another, tear apart cosmic structures and erase the visible universe piece by piece. In 100 billion years, the sky will be dark, other galaxies receding so fast their light can no longer reach us. The cosmos will appear empty even though it is still expanding faster than ever. Dark energy then is both creator and destroyer, the force that ensures the universe never stops evolving, but also the one that guarantees its eventual solitude. Whether it comes from quantum fluctuations, hidden dimensions, or the pull of a parent universe, one truth remains. The vacuum is not nothing. It is a field of pure potential, the silent engine behind everything that moves. And perhaps when the next generation of universes is born inside black holes, that same field, that same vacuum energy will ignite their expansion as well, just as it does ours now. Because in the grand cycle of cosmic creation, even emptiness is never truly empty. For most of human history, we looked at the night sky and saw chaos stars scattered at random across a black void. But with modern telescopes and powerful simulations, we've begun to see something extraordinary. The universe isn't random at all. It's woven into a vast and intricate structure, a network of galaxies and voids that stretches across hundreds of billions of light years. It's called the cosmic web, and it may be the closest thing the universe has to a skeleton. When astronomers mapped the positions of hundreds of thousands of galaxies, they found a surprising pattern. Galaxies don't fill space evenly. They gather in clusters connected by long, thin filaments of matter, with enormous empty regions, cosmic voids in between. If you could step outside the universe and look back, it would look like a glowing web of light, each filament spanning hundreds of millions of light years, each knot a cluster of galaxies, each void a dark abyss where almost nothing exists. This pattern didn't appear by accident. It's the natural result of gravity shaping the early universe. After the Big Bang, tiny quantum fluctuations in the density of matter grew under their own gravity, pulling gas and dark matter together into filaments. Over billions of years, these filaments thickened galaxies formed within them, and the structure we see today emerged a network of unimaginable scale, governed by simple physics and self-organization. Computer simulations like the Millennium Run and Illustrious projects have recreated this process in stunning detail. They show how the web evolves, how filaments stretch, twist and feed gas into galaxy clusters, fueling star formation and black hole growth. It's a living system, dynamic and interconnected. Each galaxy, including our Milky Way, is not an isolated island, but a node in this cosmic network fed by invisible streams of matter that flow through space like rivers of light. Even more remarkable, the large-scale pattern of the cosmic web looks mathematically similar to biological and neural networks. When scientists compared maps of the universe to high-resolution scans of the human brain, they found that both share similar distributions of nodes and connections. On vastly different scales, one measured in centimeters, the other in billions of light years, both systems follow the same statistical laws of organization. It's as if nature from neurons to galaxies follows a single blueprint for complexity. That similarity is more than coincidence. Both brains and cosmic webs are shaped by the balance between expansion and connection, between energy flow and structural stability. In the brain, electrical signals travel through networks of neurons, strengthening connections that carry information. In the cosmos, gravity pulls matter into filaments while dark energy pushes it apart. The result is a tension, a dynamic equilibrium that sculpts structure across all scales. In both cases, order emerges not from design but from interaction. The dark matter that makes up most of the universe's mass is the invisible scaffolding of this web. Though we can't see it, we can detect its presence by how it bends light from distant galaxies, a phenomenon known as gravitational lensing. These distortions allow astronomers to trace the hidden filaments of the web, revealing that dark matter extends far beyond the visible boundaries of galaxies, linking them together in a vast interconnected lattice. But here's where the mystery deepens. The cosmic web doesn't just organize matter, it may also organize information. Some physicists now suspect that the universe's large-scale structure could reflect deeper principles of information flow similar to the way quantum entanglement connects particles across space. If space itself emerges from the geometry of information as theories like it from qubit suggest, then the cosmic web might be the macroscopic echo of that microscopic network, the universe's own circuitry scaled up to cosmic dimensions. In that sense, every filament, every cluster, every void is part of a single system of balance, a universe constantly negotiating between attraction and expansion, between order and chaos. The galaxies are not scattered randomly. They're tracing the invisible shape of space-time itself, the way iron filings reveal the field of a hidden magnet. And perhaps that field, the geometry of the cosmos, extends beyond our universe entirely. If black holes give birth to new universes, then each child universe may grow its own web of galaxies just as ours did. The pattern could repeat endlessly, fractal-like each level, echoing the same fundamental design. The structure of everything from quantum foam to galactic filaments might be self-similar across all scales. When you zoom out far enough, the universe begins to look less like a chaotic explosion, and more like a single organism expanding, branching, and evolving. A cosmic web that thinks in a sense not because it has a brain, but because it follows the same principles that govern every system capable of complexity and self-awareness. We are tiny parts of that web, a spark of consciousness within one of its filaments, briefly aware of the structure that birthed us. When we map the sky, when we simulate the universe, we are watching the cosmic web contemplate itself. We tend to think of empty space as smooth, continuous, and silent. A calm, black ocean stretching infinitely in all directions. But that image is an illusion. The closer we look, the more it dissolves into chaos. At the smallest scales imaginable, space itself begins to boil. This is the realm of quantum foam, the restless foundation of the universe, where the very geometry of reality flickers in and out of existence. To understand this, we have to leave behind every human sense of scale. Shrink 1,000 times smaller than an atom, smaller than a proton, smaller than a quark, until you reach the Planck length about 10 to the minus 35 meters. It's a distance so tiny that even light, the smoothest wave we know, becomes meaningless there. At that scale, space-time ceases to be continuous. It breaks into something granular, a froth of fluctuating geometry where the distinction between space and time blurs. Physicist John Wheeler, who coined the term black hole, was the first to imagine this seething underworld. He pictured space-time as a quantum liquid, bubbling with tiny wormholes, loops and ripples that appear and vanish trillions of times per second. Each bubble represents a temporary distortion of geometry, a microscopic twist in space-time's fabric. At this level, the universe is not a stable structure. It's a quantum storm. These fluctuations aren't just theoretical. They arise directly from the Heisenberg uncertainty principle, which states that you can never know both the energy and the duration of a quantum event with perfect precision. The shorter the time scale, the greater the allowed fluctuation in energy. At the Planck scale, the uncertainty becomes so extreme that entire regions of space-time spontaneously curve, connect, and collapse. Tiny black holes form and evaporate almost instantly, flickering in and out of existence like bubbles in boiling water. To an observer at our scale, this frenzy is invisible. We see only the average result, smooth, continuous space. But mathematically, the smoothness of the universe is like the calm surface of the sea. Underneath, quantum waves are always raging. Every particle that exists, every photon that moves is riding on that turbulent ocean of probability. Physicists believe that this quantum foam is not just noise, it's the building block of everything. From it, space and time themselves emerge. When enough of these microscopic fluctuations become correlated, they form stable geometry, the space-time we experience. In this view, the universe is not built on space and time. It is built from them as if existence crystallized out of pure uncertainty. Some theories, such as loop quantum gravity, take this idea literally. They propose that space-time is composed of discrete loops, tiny quanta of area and volume woven together like threads in a cosmic fabric. These loops vibrate and interact, forming larger structures, much like atoms form molecules, and molecules form matter. To us it looks continuous, but underneath it's made of quantum pixels of reality. Others, like string theory, imagine that the fundamental elements aren't points or loops of space, but vibrating strings of energy, each with its own resonance. Different vibrations create different particles, just as different notes form a melody. The strings are embedded in space-time but also help define it. Their vibration patterns give rise to the geometry around them. In that sense, space-time isn't a backdrop, it's the instrument itself. What makes quantum foam truly fascinating is that it could explain the birth of universes in the same way that tiny virtual particles pop in and out of existence. Entire pockets of space-time might occasionally inflate instead of collapsing. One of those pockets could expand exponentially, becoming a universe of its own, complete, self-contained, and governed by its own laws. If that's the case, our universe may have originated as a single fluctuation in an infinite ocean of quantum foam, a rare bubble that didn't collapse but grew. Even now, at the heart of every black hole, space-time may be reconnecting to that same foam, the boundary between the known and the unknowable. There, the smooth equations of relativity break down and the wild randomness of quantum gravity takes over. In those moments, the universe behaves not like a static structure, but like a living, breathing quantum field, constantly creating, annihilating, and reshaping itself. We usually think of nothingness as the absence of everything. But in physics, nothingness is the most active thing there is. It's the raw potential of existence, the sea from which all being arises. Every atom, every galaxy, every thought, all of them are waves rising from that invisible foam, temporary expressions of the most fundamental chaos there is. And somewhere deep within that chaos, perhaps the next universe is already beginning to form. If quantum foam is the raw chaos beneath reality, then entanglement is the thread that weaves that chaos into order. It's one of the strangest and most beautiful ideas in all of physics, the discovery that two particles, no matter how far apart they are, can remain connected, as if space itself didn't exist between them. At first this seems impossible. How can something happening here affect something on the other side of the galaxy, instantly without any signal passing between them? Even Einstein called it spooky action at a distance. But it's real. Entanglement has been observed, tested, and confirmed countless times in laboratories across the world. It's not a quirk of theory, it's how the universe actually works. Here's how it happens. When two particles interact, say two photons or electrons, their quantum states become linked. Measure one and the other responds instantly, no matter the distance. Their spins, polarizations, or momenta are no longer independent, they form a single shared quantum system. Separate them by meters, kilometers, or light years, and the link remains. It's as though they're two ends of the same invisible string. In classical physics, information travels through space. In quantum physics, information is the fabric of space. Entanglement doesn't send messages faster than light. It simply shows that distance at the most fundamental level is not what we think it is. What we call space might be nothing more than the network of relationships between entangled systems. This idea has led to one of the boldest theories in modern physics, that space-time itself emerges from entanglement. Physicists like Juan Maldacena and Mark van Ramsdonk have proposed that the geometry of the universe, its shape, curvature, even its continuity is built from the pattern of quantum connections linking all particles. When particles are entangled, space between them becomes connected. When entanglement breaks down, space itself can tear apart. In 2013, Maldacena and Leonard Susskind introduced a simple but profound equation, IA = IPR. It means that every Einstein-Rosen bridge, the kind of wormhole predicted by relativity, is equivalent to an Einstein-Podolsky-Rosen pair, an entangled system. In other words, a wormhole is entanglement made geometric. Two black holes connected by a wormhole are like two particles in an entangled state, two manifestations of the same underlying connection. This changes everything. It means that the universe might be a vast cosmic network of entanglement, a web of relationships that generates the very structure of space and time. Wherever there's entanglement, there's a bridge. Wherever entanglement fades, the bridge collapses. Reality itself could be nothing more than the topology of these connections. Even the inside of a black hole may not be a hidden void, but an entangled region of space connected to the outside world through quantum geometry. The information that falls into a black hole might not vanish. It could remain encoded in the entanglement between the horizon and the universe around it. That's how the black hole information paradox might be resolved, not by destroying information, but by redistributing it through an invisible network that spans space-time. On a cosmic scale, this picture becomes even more extraordinary. If entanglement defines the structure of space, then the large-scale web of galaxies we see, the cosmic web, could be the macroscopic shadow of a much deeper quantum web beneath it. Every filament of matter could correspond to regions of high entanglement, while the vast cosmic voids could be places where entanglement is sparse. In that sense, the structure of the universe is a reflection of its quantum relationships. But the story goes even deeper. Some researchers propose that consciousness itself, the ability to experience, to process, to connect, might arise from patterns of entanglement within the brain's quantum systems. If true, then the same principle that binds particles could also bind thoughts, another manifestation of nature's tendency to connect everything it creates. Entanglement doesn't just link particles, it links realities. It ties together the smallest and the largest, the microscopic and the cosmic, the physical, and perhaps even the experiential. It's the universe's way of keeping its parts in sync, of ensuring that no matter how far it expands, it never truly comes apart. And maybe that's the real secret of existence. The universe isn't held together by forces but by relationships. Gravity shapes space, but entanglement creates it. What we see as separation is just geometry beneath it all. Everything remains connected. We are not observers looking out into a distant cosmos. We are strands in the same quantum web bound by threads of information that extend across the universe, invisible yet unbreakable. And when we study entanglement, we are not just studying physics. We are studying the language the universe uses to keep itself whole. If entanglement is the invisible thread that ties the universe together, then wormholes are its physical expression, bridges in the geometry of space-time itself. They are the literal folds in the cosmic fabric, the tunnels through which two distant points in the universe, or even two separate universes, might be connected. In 1935, Albert Einstein and Nathan Rosen discovered something remarkable hidden inside the equations of general relativity. They found that under certain conditions, space-time could form a kind of tunnel connecting two regions, a bridge linking one side of a black hole to another. They called it an Einstein-Rosen bridge. Today we know that concept by a more evocative name, a wormhole. At first it was just a mathematical curiosity, a strange but consistent solution to Einstein's equations. But as physics evolved, the idea began to take on new meaning. If space-time is a flexible fabric, then under extreme conditions it can bend not just around objects but through itself. Imagine taking a sheet of paper and folding it until two distant points touch. That's what a wormhole does to the universe. It shortens the distance between places not by moving through space, but by changing the shape of space. There are two kinds of wormholes. Non-traversable ones like those predicted by Einstein and Rosen, which collapse too quickly for anything to pass through, and traversable wormholes, theoretical constructs that could in principle allow travel between points in space-time. To keep a wormhole open, however, you'd need something that defies ordinary physics. Negative energy density, a kind of anti-gravity field that pushes space apart instead of pulling it together. Quantum theory suggests this might not be entirely impossible. The same quantum fluctuations that create virtual particles in the vacuum can also create regions of negative energy, fleeting pockets that counteract gravity. Physicist Kip Thorne, working in the 1980s, explored whether such energy could stabilize a wormhole long enough for a traveler, or even a signal to pass through. His work inspired not only scientific research, but also the most realistic depictions of wormholes in fiction, including Interstellar, where a wormhole near Saturn opens the way to distant galaxies. But in reality, traversable wormholes would be delicate beyond imagination. Even the tiniest disturbance could make them collapse. They would likely need to be microscopic, smaller than atoms, unless held open by exotic forms of matter or energy we have yet to discover. Still, their existence in theory is deeply meaningful. It suggests that connectivity in the universe isn't limited by distance. Space can connect to itself in ways that defy intuition. Because at the deepest level, space is not a container, it's a network of relationships. This brings us back to the principle ER-EPR, the idea that every wormhole is equivalent to a pair of entangled particles and vice versa. In that view, the wormhole isn't a tunnel through which things move, it's a geometric representation of quantum connection. Entanglement and wormholes are two sides of the same coin, one described by quantum mechanics, the other by general relativity. Together they may be the key to uniting the physics of the very small and the very large, a bridge between quantum theory and gravity itself. If that's true, then every entangled particle in the universe, every photon, electron or atom could be connected through microscopic wormholes. They wouldn't be tunnels we could see or travel through, but quantum bridges binding the entire cosmos into a single coherent whole. The universe might literally be stitched together by wormholes, a web of geometric shortcuts that hold space-time in place. Some theories go further. If our universe was born inside a black hole, then the mouth of that black hole, its event horizon, could connect to another region of space-time. The interior of our universe itself. That means the birth of a universe and the formation of a wormhole are the same event viewed from different sides. From the outside, its collapse. From the inside, its creation. Physicists are beginning to explore how this could be tested. In 2022, researchers at Caltech simulated a tiny wormhole using quantum computers, not a physical tunnel, but a correspondence between two entangled systems that mimicked the behavior of space-time connection. It was the first experimental hint that the geometry of space might truly emerge from information that wormholes and entanglement are not metaphors, but mathematics. If future theories confirm this, it would mean that information flow, not matter not energy, is the most fundamental thing in the universe. Space-time and gravity would all be consequences of how information connects and moves. Wormholes would be the visible footprints of those connections, the universe's wiring diagram. Perhaps that's why black holes, which are the densest storage of information known, sit at the heart of galaxies. They're not just cosmic graves, they're the nodes of the network, the routers of space-time. And if universes can form inside them, then wormholes are not just passages between regions of space. They are bridges between generations of reality. Each black hole could be the seed of a new universe. Each wormhole the umbilical cord connecting parent and child. And in that endless process of connection, the universe ensures that nothing, not even space-time itself, is ever truly isolated. At the edge of every black hole lies one of the strangest boundaries in the universe, the event horizon. It's a one-way surface, a line in space-time that divides what can be seen from what can never be seen again. Once you cross it, even light cannot escape. But to a physicist, the event horizon is far more than a point of no return. It is a mirror, a quantum surface where information is stored, reflected, and perhaps reborn. For decades, black holes were thought to destroy information. Anything that fell inside a star, a planet, a photon, or a message was believed to vanish completely, leaving only mass charge and spin behind. This idea clashed violently with quantum mechanics, which insists that information can never be lost. In quantum theory, the universe evolves in perfectly reversible steps. If information could disappear, the fundamental equations of reality would break. This tension became known as the black hole information paradox, and it haunted physics for nearly half a century. Stephen Hawking himself was the first to trigger it. In 1974, he showed that black holes aren't entirely black. They emit faint radiation due to quantum effects near the horizon. Particles and antiparticles constantly pop in and out of existence in the vacuum. When one of those pairs appears near a black hole, one particle falls in while the other escapes. The escaping particle becomes real Hawking radiation, while the one that falls in carries negative energy, slowly reducing the black hole's mass. Given enough time, the black hole evaporates completely, but that created an even deeper problem. If the black hole disappears, what happens to the information about everything that fell inside? Hawking's calculations suggested it was gone forever, erased from existence. Yet that couldn't be right. Losing information would mean breaking one of the most sacred laws of physics, unitarity, the rule that quantum evolution always preserves data. It would mean that the universe at its core forgets. To resolve this paradox, physicists began to look more closely at the horizon itself. Maybe they realized the black hole doesn't destroy information, it stores it. Not inside, but on the surface. Every bit of data that falls toward the event horizon gets encoded in subtle distortions of space-time, tiny quantum vibrations known as soft hair. These disturbances record the history of everything that has ever interacted with the black hole. The interior may vanish, but the information remains painted across the surface like ink on paper. This led to one of the most profound insights in modern physics, the holographic principle. Proposed by Gerard 't Hooft and Leonard Susskind, it states that all the information contained within a volume of space can be described by data on its boundary. In other words, the universe behaves like a hologram, a three-dimensional reality projected from a two-dimensional surface. The event horizon is the surface, a cosmic mirror encoding everything within. From a quantum perspective, what happens inside a black hole may be nothing more than the unfolding of information already written on its surface. If that's true, then our entire universe could function the same way. Our cosmic horizon, the limit of what we can see, might be storing all the information that defines the reality within it. Every star, every galaxy, every atom could be a manifestation of data encoded on the boundary of the universe itself. This idea, known as holographic cosmology, transforms the very notion of existence. We are patterns in information projected into physical form. Even black hole evaporation begins to make sense under this model. As the black hole radiates, it releases not random noise, but encoded information scrambled and unrecognizable but still preserved. The process is slow, taking eons, but in principle, every bit of information eventually escapes, woven into the fabric of Hawking radiation. Nothing is truly lost, only transformed. Recent studies using quantum information theory and string theory support this view. In 2019, researchers calculated that when you account for the entanglement between the interior and the radiation outside, information never actually disappears. The total entropy follows a curve that rises then falls again, the Page curve proving that black holes respect unitarity after all. Hawking himself ultimately conceded. Black holes do not destroy information. They are processors, cosmic engines that scramble and emit it back into the universe. So what is the event horizon really? It's not a wall or a trap. It's a quantum mirror, a surface where gravity and information meet, where geometry and data become the same thing. Matter falls in, but its information reflects outward like ripples of memory on the surface of time. And if our entire universe was born inside a black hole, then the same principle applies to us. Our cosmic horizon, the edge of what we can observe, may itself be the surface of a higher dimensional black hole, encoding everything that exists within. We are not looking out at the universe. We are looking from inside its reflection. In that sense, reality is not a thing that exists in space. It's a story written on a boundary playing out as light matter and time within. The horizon is not the end of the universe. It is where the universe begins. What if space itself isn't fundamental? What if it's not something the universe has, but something the universe computes an emergent property that arises from the way information connects? That's the question at the heart of a growing revolution in theoretical physics. The idea that geometry is made of information. The concept sounds abstract, almost philosophical, but it's rooted in hard mathematics. It began with a simple insight. Everything we observe, particles, fields, energy. Even space-time can be described as patterns of information. In quantum mechanics, every particle is represented by a wave function, a probability distribution that tells us what we can know about its state. When particles become entangled, their wave functions merge, sharing information across distance. Those links form a network, an invisible web connecting everything in the universe. Now imagine that this network is not just within space, but defines space. Where entanglement is strong, points in the network are close. Where it's weak, they drift apart. In this picture, distance itself is nothing more than a measure of how much information two regions share. Geometry is the map of entanglement. This idea has been explored most famously through the ADA-CFT correspondence, a breakthrough proposed by physicist Juan Maldacena in 1997. It describes a universe, an anti-de Sitter ad space, that's equivalent to a lower dimensional quantum system living on its boundary. Everything inside that universe, its space, its time, its gravity, can be perfectly described by information encoded on the boundary. In other words, space-time itself can be rebuilt purely from entanglement patterns among quantum bits or qubits. This is the holographic principle made precise. Physicist Mark van Rumsdonk later expanded this vision. He showed mathematically that if you gradually reduce entanglement in a quantum system, the corresponding space-time geometry begins to fall apart. Separate the entangled regions completely and space itself tears into disconnected pieces. Re-establish the entanglement and the geometry reconnects. In this way, entanglement doesn't just exist in space, it creates space. It's the stitching that holds the universe together. This perspective reframes everything we thought we knew about existence. Gravity in this context isn't a fundamental force, it's a byproduct of how information organizes itself. Einstein's smooth geometry of space-time is the large-scale shadow of a deeper discrete quantum web. At the smaller scales, reality might look less like a continuum and more like a vast computational network, a matrix of information links forming and breaking billions of times per second. The building blocks of this reality are not atoms or strings, but qubits, units of quantum information. They can exist in superpositions, entangle with each other, and encode every possible configuration of the universe. From their interactions, patterns emerge, and those patterns, when viewed at large scales, become the geometry of space and the flow of time. This is the idea encapsulated in the phrase coined by John Wheeler, it from bit, meaning everything that is every it in the physical world comes from information from the yes-no binary logic at the heart of quantum mechanics. Today, researchers have refined that into it from qubit, not just binary choices, but full quantum correlations. In this framework, space-time isn't a stage where physics plays out. It's a product of the play itself, the end result of information interacting with information. This viewpoint bridges the deepest divide in physics between the smooth curvature of relativity and the discrete probabilities of quantum theory. Instead of trying to force one to fit inside the other, It suggests they're both approximations of something deeper. The geometry of information flow, gravity describes how that geometry bends. Quantum mechanics describes how it's encoded. Together they describe how reality computes itself. If this picture is right, then the universe is a kind of quantum computer, not one built of circuits and chips, but of fundamental bits of information whose interactions generate everything we experience. Every photon that travels, every atom that vibrates, every black hole that forms is part of that computation. Even the laws of physics might not be written into reality from the beginning. They could be the emergent rules that arise from the stable organization of information. And just as a hologram projects a three-dimensional image from a two-dimensional film, our entire universe may be a projection of data encoded at its boundary. Perhaps the event horizon of the black hole that birthed us. Inside we experience space-time and motion. Outside it's just information, a perfect mirror of everything we are. This doesn't make our world less real. It makes it more profound, because it means that reality isn't made of matter or energy. It's made of meaning, the relationships between bits of information that together form the grand geometry of existence. We are patterns within that geometry, local concentrations of information that have become self-aware. And when we seek to understand the universe, we are not decoding something foreign. We are a part of the computation of the universe thinking about itself. For centuries, humans believed that the universe meant everything. All that exists, all that ever could exist. But modern physics may have shattered that assumption. Our universe, it turns out, might be just one bubble in a vast cosmic sea, one reality among countless others, each with its own laws, constants and dimensions. This is the multiverse, a landscape of universes beyond universes. The idea sounds like science fiction, but it arises naturally from several of the deepest theories in modern physics. In fact, it might be harder to explain why there would be only one universe than to explain why there could be infinitely many. The first hint came from cosmic inflation, the brief but extraordinary moment right after the Big Bang, when space expanded faster than the speed of light. Inflation wasn't just expansion, it was exponential growth driven by a field of pure energy known as the inflaton. When that field decayed, it released the energy that formed matter radiation and the universe we live in. But inflation doesn't have to stop everywhere at once. In most models, it keeps going indefinitely in some regions, creating a process called eternal inflation. In this scenario, new pockets of space-time, new universes are constantly forming in an ever-growing cosmic foam. Each one expands, cools, and develops its own laws of physics. Our universe is simply one of those bubbles. If inflation is right, then the multiverse is not just possible, it's unavoidable. Each bubble universe would be causally disconnected from the others, sealed off by distances that grow faster than light can travel. We could never visit them, but their existence would follow directly from the mathematics of space-time. They're not science fiction worlds, they're parallel outcomes of the same physical process that gave birth to us. Another source of the multiverse comes from string theory, which describes the fundamental building blocks of the universe not as particles, but as tiny vibrating strings. These strings can exist only in higher dimensional spaces, typically 10 or 11 dimensions, and the way those extra dimensions curl up determines the physical constants we observe. The charge of the electron, the strength of gravity, the mass of particles. But there are many ways to curl up those dimensions, not just one, but perhaps 10 to 500 possible configurations. Each configuration could correspond to a different universe with its own version of physics. That's the string landscape, a staggering multiverse of possibilities, all consistent with the same underlying theory. To some physicists, this is unsettling. If everything's possible somewhere, how can we explain why our universe looks the way it does? Why is the strength of gravity so perfectly balanced that stars can form? Why is the cosmological constant so small, allowing galaxies and life to exist? The answer may lie in anthropic selection. We observe this universe because it's one of the rare ones where observers like us can exist. In the infinite landscape of universes, most are sterile, too dense, too empty, too unstable. Only a few produce conditions mild enough for complexity to emerge, and we naturally live in one of those few. But there's another possibility, one that connects directly to our earlier journey. If universes can be born from black holes, as some models suggest, then each black hole in our cosmos could spawn a new universe on the other side of its horizon. That means every universe could be both a child and a parent in an infinite family tree of realities. In that picture, the multiverse isn't a chaotic swarm of disconnected worlds. It's an evolving network, a cosmic genealogy, where each generation inherits the constants of its ancestors with slight variations. Over unimaginable timescales, this process could resemble natural selection. On a cosmic scale, what physicist Lee Smolin calls cosmological natural selection. Universes that produce many black holes give rise to more offspring universes, those that can't end their line. Over billions of generations, universes evolve their constants, slowly drifting toward values that maximize black hole formation and therefore reproduction. If that's true, then our universe's physical laws are not random. They are the optimized result of cosmic evolution. This paints a breathtaking picture. Imagine an infinite hierarchy of universes, each existing within the black holes of others, connected like nodes in a self-sustaining web. Some expand quickly, some collapse early, some never form matter at all. But all of them share a common origin, the quantum fabric that gives birth to space-time itself. From our limited vantage point, we can never see beyond our horizon. We may never detect the other bubbles or touch the universes born inside black holes, but the physics suggests they are there not as fantasy but as consequence. We are part of something larger, a multiverse not fiction but of geometry and quantum inevitability. If that's true, then the word universe is a misnomer. We don't live in the universe. We live in a universe, one version of reality among countless others, each exploring a different way the laws of physics can unfold. And perhaps just as life asks, why am I alive? Our universe is asking the same question. Why am I the one that exists? Everything we see, stars, galaxies, light, matter, exists within 3 dimensions of space and one of time. To us that feels complete. It's the framework in which everything happens. But what if that framework itself is only part of a larger structure? A kind of membrane floating in a higher dimensional ocean? This idea, once confined to mathematics, has become one of the most provocative models in modern cosmology. It's known as the brain-world hypothesis. In string theory, the universe doesn't have just 4 dimensions. It has 10 or even 11. 6 or 7 of them are compact, curled up so tightly that we can't perceive them, while the remaining 4 form the space-time we inhabit. But according to the Randall-Sundrum model proposed in 1999, those extra dimensions might not all be microscopic. Some could be vast, stretching beyond our comprehension, hidden not by size but by the fact that we're trapped inside a lower dimensional surface, a brain embedded in a higher dimensional bulk. Imagine a soap film floating within the air. To a creature living on that film, the world would seem flat and 2-dimensional. It could move forward, backward, left and right, but it would never know that up exists. That's us. Our universe is the film and the air around it. The unseen 3rd dimension is the bulk. We can move through space and time, but not beyond them. The higher dimensions exist, but we are confined to our own slice. In this picture, gravity may be the only thing that doesn't play by our rules. Unlike light or matter which are trapped on the brain, gravity can leak into the higher dimensions. That might explain why gravity is so much weaker than the other forces, why a simple refrigerator magnet can lift a paperclip against the pull of an entire planet. If gravity spreads through extra dimensions, most of its strength is diluted across the bulk. We feel only the faint residue that remains on our brain. This idea isn't just theory, it's testable. Experiments have looked for deviations in gravity's behavior at small scales, hoping to detect signs of leakage into higher dimensions. So far none have been found, but the search continues. Even the shape of our universe's expansion could hint at the presence of hidden dimensions influencing it from beyond. In the brain-world model, black holes take on an entirely new meaning. A black hole in our universe could extend into the bulk, forming a higher dimensional object known as a black string or black brain. The gravity we see is just the cross-section of this larger structure. When a black hole forms in our universe, it might also connect to or even open into another brain in the bulk, forming a natural bridge between realities. And here's where the idea becomes breathtaking. If our universe was born inside a black hole, as we've explored before, then the parent black hole could exist, not in another region of our own space-time, but in an entirely different brain. A higher dimensional space whose gravitational influence created our own. Our universe could literally be a bubble universe, expanding within a 5-dimensional bulk the inside of a higher dimensional object. Some physicists have gone further still. They imagine that what we call the Big Bang was not a singular explosion but a collision between brains. Two higher dimensional surfaces, perhaps parallel universes drifting through the bulk, eventually collided, converting kinetic energy into the heat and radiation that became our cosmos. That's the idea behind ekpyrotic cosmology, from the Greek word ekpyrosis meaning conflagration. In this view, the Big Bang wasn't the beginning of time, but a recurring event. A cosmic heartbeat as brains collide, separate and collide again. The implications are staggering. If brains can collide, they can also coexist. There could be countless parallel universes, other brains floating alongside ours in the higher dimensional bulk invisible, but close enough that their gravity might subtly tug on ours. Maybe on rare occasions a burst of gravitational energy passes between them, a faint echo from a neighbouring universe. In such a cosmos, the universe is no longer the totality of existence. It's just one surface in a vast dimensional ocean, a living membrane rippling through higher space guided by the unseen currents of the bulk. We may never directly access those extra dimensions. Our particles are light, our atoms are bound to this brain. But through gravity, the one messenger that can cross the boundaries, we might someday detect their presence. A tiny deviation in the pull of gravity, a subtle imprint in the cosmic microwave background, could be the whisper of another universe brushing against ours. And if that's true, then everything we've ever known, every galaxy, every star, every law of physics, is part of a larger architecture, a hidden scaffolding of dimensions beyond our perception, where universes are born, drift and die like waves in an infinite sea. We call it the bulk. It might be the womb of all creation, the true stage on which existence unfolds. Every great theory in physics begins with a question and ends with a boundary, a point where the math stops working, where observation becomes impossible, and where reality itself refuses to yield another secret. No matter how far we go, from atoms to galaxies, from black holes to multiverses, we always end up standing at the edge of knowledge, staring into the unknown. In the early 20th century, we reached the first such edge. Einstein's general relativity gave us a perfect description of gravity and the shape of space-time. At almost the same moment, quantum mechanics revealed the rules of the microscopic world: uncertainty, probability, superposition. Each theory works flawlessly within its own domain. Relativity rules the stars. Quantum mechanics rules the atoms. But when we try to combine them, when we ask what happens inside a black hole, or at the moment of the Big Bang they collapse into contradiction, this is the first great boundary of modern physics. We do not yet have a complete theory of quantum gravity. We have candidate string theory loop, quantum gravity, emergent space-time models, but none have been experimentally confirmed. Each is elegant, consistent, and deeply mathematical, but the universe has not yet told us which one, if any, is true. Part of the reason is that we can't test them. The energies needed to probe the Planck scale, where quantum gravity dominates, are far beyond anything we can reach. Even our most powerful particle accelerators, like the Large Hadron Collider, operate trillions of times below that threshold. To see quantum gravity directly, we'd need an accelerator the size of a galaxy, or the ability to look inside a black hole, something nature itself forbids. That brings us to the second boundary, the horizon of observation. No telescope can see beyond the cosmic microwave background, the faint afterglow of the Big Bang emitted when the universe was just 380,000 years old. Beyond that lies the opaque era before light could travel freely. We can model it, simulate it, infer it, but we cannot see it. The first instant of creation, the birth of space-time itself, remains hidden behind a veil we cannot pierce. Even within our own universe, there are places forever beyond our reach. Galaxies receding faster than light due to cosmic expansion are already lost to us. Their light will never reach Earth, no matter how long we wait. They still exist, but for us they are gone. The observable universe is not the universe itself. It's just the small luminous bubble of space that our instruments can access, about 93 billion light-years across, and growing smaller in proportion to the whole with every passing second. The third boundary lies not in our instruments, but in our assumptions. Our theories rely on mathematical elegance and symmetry ideas that have served us well, but might also mislead us. Perhaps the universe doesn't care about elegance. Perhaps some of our fundamental constants are not fundamental at all, but byproducts of a deeper system we haven't yet glimpsed. We may be describing shadows of a structure we can't yet perceive. Even the concept of the multiverse, as beautiful as it is, may never be testable. If other universes are causally disconnected from ours, then no light, no signal, no information can ever cross between them. That means they may remain forever hypothetical, real in mathematics, unreachable in physics. At some point we must ask, what counts as science when observation itself is impossible? And yet this is what makes physics extraordinary. The more we learn, the more we see the edges of our ignorance. Every discovery, from relativity to quantum mechanics, from dark matter to cosmic inflation, has not closed the book of reality but opened new chapters we didn't know existed. The universe seems to expand not just in space but in mystery. This humility is not weakness, it's the engine of progress. Physicists are explorers of the unseen. They map what they can measure, then push against the fog of what they can't. In doing so, they reveal that the true beauty of science isn't certainty, it's curiosity. Every horizon, every paradox, every unanswered question is an invitation to go further. We don't know what happens at the center of a black hole. We don't know what triggered inflation or whether time itself had a beginning. We don't know why the laws of physics are as they are or whether they could have been different. But that's what keeps us moving, the knowledge that there's more to know. The edge of knowledge is not the end of understanding. It's the beginning of wonder, and in that sense our ignorance is sacred, because it is proof that the universe still has secrets left to tell. The universe is not eternal in the way we once imagined. It had a beginning and it will have an end. The stars that now light our skies, the galaxies that fill our telescopes, even the atoms that make us, all of them are temporary. Time, it seems, has a direction, and that direction points toward entropy. Entropy is the measure of disorder, the gradual spreading of energy into forms that can no longer do work. From the moment of the Big Bang, entropy has been rising. Every star that burns every galaxy, that spins every atom that moves all, are part of the universe's long march toward equilibrium. One day that march will end. In the far future, trillions of years from now, the stars will begin to die. The great furnaces of hydrogen and helium will run out of fuel. First, the red dwarfs. The smallest, longest-lived stars will fade into black embers no longer shining. White dwarfs will cool and crystallize into cold, dark spheres. Black dwarfs invisible against the endless night. The galaxies will dim. Only the occasional flare of a dying star or a colliding neutron core will break the silence. As time stretches on, gravity will continue its quiet work. Galaxies will merge into giant ellipticals, then collapse around supermassive black holes. Those black holes will become the last anchors of structure in an increasingly empty cosmos. Vast wells of gravity surrounded by oceans of darkness. But even they are not eternal. According to Hawking radiation, black holes slowly lose mass as they emit quantum particles. It's an unimaginably slow process. A stellar black hole might take 1067 years to evaporate completely. A supermassive one, 1,000 years or more. Yet eventually they too will vanish, leaving behind nothing but faint whispers of radiation, the last breath of matter returning to the quantum sea. At that point, the universe enters its final act, the era of heat death. All energy becomes evenly distributed. There are no stars, no galaxies, no light. Only a thin mist of photons, neutrinos and particles drifting through an ever-expanding void. Temperature approaches absolute zero. Time itself loses meaning because nothing changes. The universe reaches maximum entropy, the ultimate stillness. But even that might not be the end. In quantum physics, nothing is truly static. Even the vacuum seethes with fluctuations, tiny bursts of energy that appear and disappear. Given infinite time, those fluctuations can produce anything, even in principle, entire universes. This leads to one of the strangest possibilities in cosmology, the quantum resurrection of existence. In this scenario, long after the last black hole fades, random quantum fluctuations could assemble a patch of space-time dense enough to trigger inflation again. From that spark, a new universe would be born, expanding, cooling, forming stars and galaxies, and perhaps even new forms of life. It wouldn't be our universe, but it would be a universe born from the ashes of entropy. The cycle would begin again. This vision turns the end of everything into something closer to a transformation. The death of the universe might not be a final extinction, but a phase change, a quantum transition from one reality to another. Each universe could give rise to others in an endless sequence, a cosmic chain reaction. echoing across eternity. And yet the timescales are so vast that they defy imagination. If we compressed the entire history of our universe into a single year, the death of the last black hole would occur after 10 million trillion such years had passed. By then, every trace of what we know, every planet, every atom, every memory will have long dissolved into radiation. It's easy to see this as tragic, but there's also something profoundly beautiful about it, because the universe from beginning to end obeys the same simple, elegant laws. From the birth of atoms to the evaporation of black holes, everything follows the same principles of energy, entropy and quantum uncertainty. The same rules that created stars also destroy them. The same equations that birthed life will one day erase it, yet they are perfectly balanced and unbroken symmetry from alpha to omega. And maybe that balance means the story never truly ends. Even after the lights go out, the potential for creation remains written into the quantum foam beneath reality. The stage may go dark, but the script is still there waiting for the next performance. So when we ask when will the universe end, the answer might be never, it just changes form. Imagine the universe long after its last light has faded. No stars, no galaxies, no atoms, just a vast silent expanse, dark, thin and cold beyond comprehension. Even black holes, once the anchors of cosmic structure, have long since evaporated. Nothing stirs, nothing changes. This is the end of time. At first glance, there seems to be nothing left to talk about. If every process has stopped, if every particle has decayed, if even photons have stretched into infinite wavelengths, what could possibly remain? But physics whispers a strange answer: information. According to the laws of quantum mechanics, information can never truly be destroyed. It can change form, scramble dispersed, encoded in subtle correlations, but it cannot vanish. Every particle that ever existed, every event that ever occurred, leaves a kind of fingerprint on the universe. Even after the matter dissolves, those patterns of information may persist in the structure of space-time itself, a frozen record etched into the geometry of the cosmos. Physicist John Archibald Wheeler once said, "The past is theory. The future is fact, but in the deepest view of quantum reality, both may coexist timelessly, not as moments that flow, but as configurations in a vast informational landscape. When motion ends and entropy reaches its maximum, what remains is not emptiness, but structure without change, the static shadow of everything that ever was. To understand this, we need to think differently about time itself. In everyday experience, time seems to move, but in physics it doesn't move at all, it simply is. According to Einstein's relativity, all moments in time exist simultaneously within the four-dimensional block of space-time. The flow of time is an illusion of perspective, a path traced by consciousness as it moves through that block. From this point of view, the end of time is not a moment that happens. It's a boundary, a region of the cosmic block beyond which no new events occur. Everything that ever happened still exists within that structure eternally. This brings us to the idea of a timeless universe. If all states of reality coexist in the fabric of information, then even after physical processes cease the total informational structure, the wave function of the universe remains. It doesn't evolve because evolution requires time. It simply is a complete static, self-contained description of everything that ever existed, from the first flash of the Big Bang to the final whisper of heat death. A universe without motion, yet containing all motion that ever was. Quantum cosmologists sometimes refer to this as the Wheeler-DeWitt state, an equation that describes the universe as a single, unchanging quantum object. In this view, the passage of time is not fundamental. It's an emergent illusion that appears only to observers within the system. When entropy reaches its maximum, the illusion dissolves, leaving only the timeless quantum whole. But even this may not be the true end. Some theories suggest that deep within the vacuum, even after heat-death fluctuations of quantum geometry continue the eternal foam beneath existence. In that foam, information may recombine, giving rise to new regions of space-time, new universes, new beginnings. The end of one timeline becomes the seed of another. In the grand network of reality, there are no dead ends, only loops. If that's true, then nothing is ever truly lost. Not matter, not energy, not even meaning. The universe doesn't die, it folds back into itself. Its information, the sum of all things, persists in the quantum foundation, like a library that cannot be burned, only rearranged. And what about us? We are made of that same information. Every thought, every atom, every photon in our bodies is part of the same universal computation. When we die, that information returns to the field from which it came. When the universe dies, it does the same. We in the cosmos share the same fate. Transformation, not annihilation. In the final silence, there are no clocks. No before or after. No expansion, no decay, no motion. Just the totality of everything. All possible histories, all possible futures frozen into the same eternal equation. A universe without time yet containing all time within it. And perhaps from that quiet foundation a new fluctuation begins to stir. A ripple in the foam, a spark of quantum noise. The birth cry of another universe, rising once again from the stillness. After everything we've learned, the stars, the galaxies, the black holes, the quantum foam, the multiverse, one question remains. It's not a question about how the universe works or when it began. It's deeper than that. It's the question that underlies all others. Why does anything exist at all? Every equation we've discovered, every law of nature we've written down, describes how something behaves, not why it is there. Physics can explain the mechanisms of creation, but not the reason for creation. We can trace the universe back to its first instant, the quantum fluctuation, the inflation, the birth of time itself, but beyond that, there is silence. In principle, nothing should be the simplest state. No space, no time, no energy, no laws. And yet here we are, surrounded by a vast complex cosmos filled with structure and life and consciousness. Somehow something exists when it didn't have to. Why? Some physicists have tried to answer this in purely natural terms. They point out that in quantum mechanics, even nothing is unstable. The vacuum isn't truly empty. It's a seething sea of fluctuations, constantly creating and annihilating particles. Given enough time, one of those fluctuations could produce a self-sustaining universe, a bubble of space-time that inflates and evolves. In that sense, existence is inevitable. The question isn't why something, but how could there not be something? Others suggest that existence itself might be a mathematical necessity. If reality is built on logic, then perhaps all consistent mathematical structures must exist in some form. Our universe could be one of those structures, a self-consistent solution to the equations of being. In that case, the reason the universe exists is because it can. But there's another perspective, one that blurs the boundary between physics and perception. Perhaps existence and observation are two sides of the same coin. In quantum theory, nothing is real until it's measured, until it interacts, until it's observed. So maybe the universe exists because it observes itself. Consciousness in this view isn't a byproduct of the universe. It's a fundamental feature of it, the mirror through which reality becomes aware. If so, then our presence here, thinking, asking, wondering, isn't accidental. We are not separate from the universe looking in. We are the universe looking back at itself. Every thought, every equation, every act of curiosity is a continuation of the same process that began at the Big Bang. The process of the cosmos becoming conscious of its own existence. Still, even that doesn't fully satisfy the question, because at the deepest level we must confront a truth that no theory can escape. Physics can describe everything within the universe, but not why there is a universe to describe. Every equation needs a context, every cause needs a framework in which to act. And that framework, the totality of existence, has no outside. Maybe the universe exists for no reason at all. Maybe it simply is. In the same way that the number p exists or that logic exists, perhaps existence is not something that needs explaining. Perhaps it's the starting point of all explanation. And yet the fact that we can ask the question at all may itself be the answer. Because to ask why does the universe exist is to be part of a universe capable of questioning itself. A universe where matter has organized into mind. And mind has turned around to ask about matter. In that loop, existence completes itself. The question and the answer become the same thing. In that sense, the cosmos may not need an external creator, a hidden reason, or a first cause. It may be self-sustaining, a closed circle of being governed by laws that give rise to themselves, just as geometry gives rise to space, or information gives rise to time. A universe that exists because it can, and that asks why because it must. And so, as we reach the end of this journey from black holes to quantum foam, from the birth of space to the death of time, we're left not with a final answer, but with a deeper awareness, that to exist to wonder and to seek understanding is itself the universe fulfilling its purpose. Because in the end, the universe doesn't need a reason to exist. It only needs to be aware that it does, and that awareness is us.